Hello everyone, in this tutorial we're going to use AI and machine learning, specifically a neural network, to classify stars from hottest to coldest, or from O class to M by exploring features in a dataset to predict what class a star belongs to. In this stellar classification diagram, we can see that the hottest class is O and the coldest is M. What we also realized just by looking at the molecular structure of each class, there's a close relationship between what the star is made of and its relative temperature, because some elements burn hotter than others based on basic laws of chemistry. One thing you notice in this first row belonging to class O, which is the hottest star type, is the fact that the majority of its molecular structure is made of hydrogen, a highly flammable substance that burns swiftly and completely without residues, which explains why it is the hottest class. You can also notice that usually the stars of that class are blue or violet, which is what we will explain in a moment. From another angle, there's a correlation between the color of a star and its temperature, which has to do with the frequency of light emitted from that star. We already know that in the light spectrum we have a wide range from ultraviolet to infrared, the latter being the highest frequency of light and the former the lowest. There's basically a direct relationship between the frequency of light coming from a star and how hot the star is. To give you a simple example for that, when you're lighting a fire in the woods, I wouldn't recommend it unless it is professionally done, of course, in a contained environment, but you notice the fire color is red and the heat of that fire would not be intense, since you can easily sit close to a huge fire pit and cook something while warming yourself. However, when using gas to cook something, so for the first example you notice here in this image, yellow and red torch, or red flame so to speak, when using a wood fire. Meanwhile, and which is less hot than gas fire, for the gas being burned, when using gas to cook something, for instance, in the kitchen, the color of the gas torch would be blue. So it is a high frequency flame, unlike the wood fire. The heat is so intense in this case, and the size of the torch is so small to protect the person that is cooking next to it. Still, it is enough to generate more heat than a wood fire. Another example, a thunderstrike is an electrostatic discharge, which is one of the most rapid fires, having a very high frequency and a bluish color. Meanwhile, a match fire is slow, its main fuel is wood, and hence we observe a red flame that slowly consumes the wood. Plus there is residues, by the way, when it's done burning. So meanwhile, a substance that is mainly gas consumes fast, almost without residues, like kerosene. The flame would have a blue profile because most of the components burn up without residues. Looking at this graph from Wikipedia, we see the relationship between the wavelengths and the spectrum energy. What stands out in this graph is the high temperature translating into high spectral energy, specifically for shorter waves or high frequencies, because the frequency is inversely proportional to the wavelengths. We know that from lambda equal v over f. V, of course, being the speed of light, but it's not the speed of light in empty space. It is in a contaminated environment. We notice that the frequency and wavelengths are indirectly proportional. So these are the different classes for the stars. A class O being the hottest class of stars temperature wise, of course, all the way to M being the coldest one. And you notice for O the color is blue leaning to violet, but for K and M it becomes yellow all the way down to red, even to infrared, okay, as it becomes cooler. What we see in this picture is the Hertzsprung-Russell diagram. Hertzsprung and Russell, through observation, classified different stars based on the luminosity and temperature of these stars. What they found out is that we have what we call the main sequence of stars, being this curve here, where it basically follows through the main analogy, which correlates the temperature with the intensity of luminosity. And you have three outliers basically, which are the supergiants, giants, and white dwarfs. Now, for these three clusters or outliers that don't follow this analogy, like white dwarfs that are hot but not too luminous, white dwarfs are the remnant of a star after a supernova explosion. They are actually the core left after the death of that star, but still it is intensely hot but not too luminous, not too bright. For the supergiants and the giants, these are cold but highly luminous, also remnant of the stars. According to Observatory Astro Utah.edu, white dwarfs are mainly composed of oxygen and carbon created by the fusion of hydrogen and helium. And this is what explains how they happen to be extremely hot, because hydrogen and helium are gases that burn intensely. On the other side, supergiants and giants contain heavier components, such as metals. That's why they burn slowly and have a colder temperature, although they appear to be brighter, which gives them a high luminosity. So these three groups are the outliers from the main sequence. In this example, we're going to use a neural network in order to predict the star class for a specific sample of observation. So how does a neuron work at first? A neuron gets an electrical signal in the dendrites. When the signal's amplitude crosses a certain threshold, the neuron will be activated or fired by releasing an impulse to the next neuron connected to it, and this is what creates the thought process. This is another representation, more elaborate, for a neuron. You see the dendrites. This is called the axon in the middle, which is the connecting wire from the head of the neuron all the way to synapses. The synapses would be connected to another neuron via the dendrites, and this is how an electrical signal, electrochemical biologically, would be transmitted from one neuron to another. You have also the myelin sheath. What the myelin sheath does is it acts as a barrier for electrical signals so that you won't have a surge of electrical signals from one neuron to another next to it. This is a neural network. This is what it looks like. So you see nodes at the input, one node at the output, and all of these nodes are connected to each other. Each one connected to the other ones at the next stage. Namely, you have three layers. You have an input layer, hidden layers, and output layer. So a neural network is made of three main stages. The first stage is the input layer or entry stage for the neural network, or input layer, where an input is fed to the network to be processed and analyzed. The second stage is the hidden layers, where one or multiple layers, based on the depth of the network, are activated or not to release a signal in a specific direction. The signal will be added up in a direction of one node or another, and the final layer, the output layer, to activate one node or another. Okay, each node associated with one different result. In this current image here, we only have one node in the output, so this neural network would give a binary result, activation or not, such as true or false, yes or no. Okay, this is a simple neural representation of one neuron. The circle in the middle is the neuron actually. The neuron is fed with an input, and based on the magnitude of the input multiplied by the weight, by the way, which is a numerical value connecting the input to the neuron, okay, based on that the neuron is activated or not, and it fires when the input signal crosses a certain threshold. and this is the formula that you would get. The output is equal the input value multiplied by weight plus a bias. The bias, by the way, is used to alter the activation threshold of a neuron. When having multiple inputs, such in this case, each input signal is multiplied to the weight connected to it. That input is added up to other inputs multiplied to their own weight of connection between them and the neuron. And finally, all of these would be added up plus the bias of the neuron, hence giving or leading to the following result or outcome, which is y. The output is equal to weight of the first connection multiplied by the input to that neuron plus weight of the other connection connecting the second input to the neuron plus finally bias. So y equal x1 times w11 plus x2 times w21 plus the bias. Okay, you see here multiple connections, multiple neurons in the hidden layer. So that's why you have multiple outputs. Of course, we presented the equation for only one, which is y11, but multiple outputs mean multiple potential results or answers. You have two inputs, so each input again has a weight on its connection to the neuron. So w11 meaning this is the weight of the first input to the first neuron. w12, that's the weight of the first input to the second neuron, and so on and so forth. For w21, this is the weight for the second input to the first neuron. w22, weight of the second input to the second neuron, and finally w23 is the weight for the second input to the third neuron. And here, of course, y32 also in the same way. This is the output from the third neuron to the second output, okay, to the second option, the second answer. This leads us to form the following matrices. Y, W, and X, and also B, of course, are formatted into matrices given that Y is actually the output having different exit nodes or different potential results. Then you have W, which is the matrix holding different weights, each weight belonging to one wiring between an input and a node. X is the matrix carrying different inputs to the network. And finally, B is the matrix for different biases belonging to different neurons, to different nodes. So finally, Y, large Y, is equal W1 times X1 plus W2 times X2 all the way to Wn, Xn plus the bias. Bias here is matrix, by the way, plus B1, B2, B3, okay? Finally, we're going to talk about the activation sigmoid. Actually, the activation can be different types of functions. You have the sigmoid, the tanh, you have rectified linear unit. We are only representing the sigmoid, which is A equal 1 divided by 1 plus E minus X, and this is the graphical representation. For X equals 0, A equal 1 divided by 1 plus exponential of 0, which is 1. Anything placed to the power of 0 would give you 1. So it would be 1 over 2 or 0.5. This is the activation threshold. So any number above that, because you know E minus infinity tends to 0. So when X goes to a large number, A, the activation function, would start leaning toward 1, which is a perfect signal. However, the activation starts when A crosses 0.5 or when A is equal to 0.5 something, okay? Now, for negative numbers, you would have a positive exponential, so the sigmoid would lean toward 0. This is how it works. And this would be the function by which the neuron activates. Again, we have other different functions that work in similar ways. Okay, the dataset we're going to use for that purpose is actually taken from Kaggle. Its title is star dataset to predict star types, although we're going to use it to predict the class, not the star type, but it is the same concept. So I will list, of course, the link for that dataset in the description below. In order to download it, of course, you click on download. And I've actually downloaded it and extracted it already to show you the dataset. This is what the dataset looks like. Now, I needed to change the titles or the field names, so to speak, a little bit, and then saved this dataset into another dataset. File, save as, star class, let's say star class 3.csv. But I'm gonna use the star class 2 I've edited before, but it is the same one. Let's go to Google Colab. We've opened a new notebook in Google Colab. This is where we are working. We'll rename it Star Class Prediction. You click on Files and we need to import the dataset. I can simply drag the dataset and drop it to the files. So let's start importing libraries. Import numpy as np, import pandas as pd, let's create a data frame, df equal pd dot read csv, and we've named it star class 2.csv. df.head to see if the columns or fields are already within the dataset, and they are. Okay, so the first row is actually the fields of the dataset. After that, let's type df.shape to see how many fields we have and how many records or rows. So df.shape 240 by 7, which means 240 records, 240 samples or measurements by 7 fields, of course. Of the 7 fields, you have 6 features. The 7th would be the target, the result. Now, if you go back to df.head, we notice something, that star color, for instance, which is a feature, has string values. We cannot afford having string values. So does the spectral class, by the way. We need to map these string values into numbers. Why? Because computers understand numbers, not string values. We cannot measure or calculate string values. That's why we need to remap them to integers, for instance. Let's check at first how many unique values star color and spectral class have. If we go here and type df star color dot unique, you have all these values are the different star colors. Spectral class dot unique, you have different values, different results for spectral class. Okay, now in this dataset you have some of the values are repeated, right? Which is not correct in the dataset. So blue-white is written in a different way and considered as being a different star color, although it is the same star color being written slightly in a different way. Okay, but we're not gonna worry about that. We're gonna consider it as being, a different star color. Although usually in a data set, these problems need to be paid attention for. We need to convert these string values into integer, so we will for spectral class as well. So let's create a color mapping array. So color mapping, color, I for I, color in enumerate, df star color dot unique. meaning get for me all the unique values for star color and enumerate them, convert them into numerical values, or map them into numerical integer values. S-class mapping or spectral class. So S-class J for J, S-class in enumerate, DF spectral class dot unique. Now let's convert the fields of star color and spectral class into these numerical values. DF star color equal DF star color dot map. We're gonna replace these string values by their mapped values. Map color underscore mapping. DF spectral class equal DF spectral class dot map S class mapping. If we type DF star color to print it to the screen, you will see all the values have been converted to integer values. Now let's create an array for the different fields. We're gonna call it cause equal, and let's paste it. Temperature, luminosity, radius, absolute magnitude, star type, star color, all the way to spectral class. We're gonna plot the relationship between the different fields, or the different features basically, and the spectral class, which is the target, to see what relationship there is between these features and the target. So for I in range 6, plt.subplot I plus 1, plt.scatter, df cause of I, df spectral class equal 0. So present for me the data on the x-axis. df cause I means df for the feature. For each df spectral class equals 0. That's on the x-axis. And on the y-axis, df spectral class, plot for me the spectral class only where this spectral class is equal to 0. Basically, what we're doing here, because if you type df spectral class dot unique, you will see we have 7 classes, okay, from O to M, as you remember. So this is what we're trying to do. We're trying to get the relationship between different features and the classes. We're gonna do the same thing for spectral class equal 1, spectral class equal 2, 3, 4, 5, and we have also 6. 6, plt.x label, plt.y label, spectral class. Finally, plt.legend, OBA all the way to M. plt.title layout and plt.show. You see the different categories, different classes are represented with their relationship to star color, star type, absolute magnitude, etc. Let me add something, plt.figure. Let me add something, plt.figure. Fig size equal, make each figure 8 by 8. It's okay because it is very small. So you see for star color, each value of star color would give you a different class or a class magnitude. Let's start pre-processing data. From sklearn.preprocessing, import standard scaler. Let's say you have values from 0 to 1000 to million. These are very disproportionate values. You have a large gap from the smallest value all the way to the largest value. So we need to fix that because they are not practical values. It's like saying and intensity of light is between 0 and 1 million, okay, so we need to change it into a more scalable value, just like when we use the logarithm in order to measure the intensity of sound in decibels. You need normalized value. So standard scaler, one of the way it works, it normalizes the values by getting the average value of all the field. Then each value in that field would be measured based on its distance from that average. Scalar equals standard scalar. Let's split right now the data frame into the features and the class. So the features are represented by x equal df dot columns of all features. Column means get all the columns minus 1. So all the columns except minus 1, meaning minus 1, by the way, represents the last column. It's like telling the data frame get me all the columns except the last one, which is, by the way, the last field 6. So it is the same thing as writing column 6. Y equal df spectral class, okay, which is the last field or the target. Let's scale the data set. X equal scalar dot fit transform df x, meaning the data frame for each of the columns mentioned here, from the first column all the way to the last column without the last one being included since it is the target. Let's run it. Now let's import TensorFlow to work with the neural network. So import TensorFlow STF. From TensorFlow import keras. From TensorFlow.keras import layers. Let's split the dataset into training and testing. What training does, part of the dataset is used to train the neural network, meaning that the neural network will rely on that part of the dataset to learn for each input the output, how the output should be given. We will split the dataset into training and testing parts. The train dataset is used to train the neural network, so the neural network would learn from the inputs how to tune a specific output to be given based on the output that was already within the spectral class. The testing dataset is used to test whether this neural network has accurate values or not, and how much is there an accuracy for that neural network. So xtrain, xtest, ytrain, ytest equal train test split x y test size for the testing equals 0.2, meaning 20% of that data set is used to test the accuracy and the loss and different parameters of that neural network. Random state equal 42, which is the rate of shuffling of that data set so that it would be randomized. Modo equal keras.sequential, and here we are building the neural network. Layers.dense can use 64. Actually, I found out that 400 happens to be one of the most accurate. So these at the entrance, you have 400 access points. Activation type equal ReLU or rectified linear unit. Input shape, the size of the input, equal xtrain dot shape 1, meaning give me the number of fields for that data set. Dot shape 0 would give you the number of rows. We are more interested in getting the number of fields. Comma, for the other empty blank space here, the number of rows, left it blank, meaning whatever number of rows, figure it out. Layers.dense 400 activation equal ReLU. Finally, layers.dense. Here we're getting the length of the different results. Okay, now at the output we have 7 options, 7 different results, right? 7 given the fact that we have 7 classes. So the number of options of results at the last stage is determined by the length of the spectral class dot unique, because the f spectral class dot unique gives you 7 options, and the activation function is the softmax function. Again, as a reminder, if I type the fSpectral class.unique, we have 7 options at the exit. So the exit layer has 7 nodes. That's why the last line is layers.dense. Get me the length of the fSpectral class.unique, which is 7 values. Also, I need to define the optimizer, the loss, the metrics. Model.compile optimizer equal Adam, or let's use RMS prop because I've checked it happens to give higher accuracies. Loss equal sparse categorical cross entropy. Metrics equal accuracy. Finally, model.fit x-train, y-train, epochs meaning cycles from forward to back propagations. So epochs equal 100, meaning try 100 times to tune the knobs of different nodes so as to fine tune the results. Batch size equal 32 and validation split equal 0.2. Finally, loss accuracy equal model dot evaluate x test y test, and we're gonna get the test accuracy. How accurate is this neural network based on the x test, and how it will work? Predict the x test dataset and compare the prediction with the target that's already a correct value within this dataset. Also, lest we forget, we need to import the sklearn model selection train test split that we can use this function. So from sklearn.model selection import train test split. Let's run it again. And we are training the model right now. And we've gotten an accuracy of 89%, which is fine. It's very good. Okay. Now, if we want to predict, we type ypred equal model.predict x test. Let's predict. Okay. So it will predict the x test. Let's get the value. Ypred equal np.argmax ypred axis equal 1. This means get for me in ypred the maximum argument and give me this argument at axis 1. We will show you. Okay, ypred, let's print it. You see? So let's work with a sample. Let's predict based on a sample. So x sample equal np.array will create an array. Okay, let's copy a specimen from above. If you go back to the data set, if I type the f.head again, we can copy these values, paste them into the array. Let's arrange the values, okay, correctly to remove the error. Now we're gonna tweak these values. Let's change these values to 1068, 0.62, let's say 0.47, 12.125 for the star type. Star color, let's say it is 8 or 4. Another thing we need to do is x sample equal x sample dot reshape 1 minus 1 to get a one-dimensional array. Before running that, actually, if you type x sample dot shape, let's run it. 6 rows and n columns. Okay, this is how it's presented. We need to reshape it. Dot reshape 1 minus 1. If I type x sample after that, dot shape 0, let's say, the shape has been converted from 6 to 1, from 6 rows to 1 row and 6 values. So we basically changed the dimension of this array to a unidimensional array. That's the point here. Alright, so let's predict based on example. Let's predict and try to assess what spectral class it would give us. So y new prediction equal modo dot predict example. Y npred equal. Let's flatten this value. So y npred equal y npred dot reshape -1 to flatten the array. We've gotten this value, you see. So it is the second class. So let's get the key to this class. We have O, B, F, something like that, right? If I type S class mapping, you have 0, 1, 2. So 1 belongs to B. But how to write it as a script to get B from Python itself? We simply loop through the end prediction. So for key value in S class mapping dot items, if val equal mp dot argmax ypred print key, and you see we've gotten B. So what this small script does is looping in S-class mapping and comparing each value of this S-class map, which has keys and values, by the way, KVP or key value pairs. So if the value is equal to np.argmax, get me the key of that value. If you print S-class mapping, we are looping through all the values here, and when we've gotten 1 equal to np.argmax, we printed the key for that value, which happens to be B, and hence we have predicted the spectral class for that arbitrary input, which is this new example. As a reminder, the accuracy for that neural network is around 89.5% or 90%.